Welcome to my channel RLD Academy. This is lecture number 1 in transient analysis of networks. In this video, I am going to discuss initial and steady state value in RC networks. Here, I'll give you a brief introduction about capacitor. And you see here, these are few practical capacitors. Those are available in market. However, basic components of capacitors is that it is having two conducting plates separated by one dielectric material like SiO2, silicon dioxide. Suppose this is one plate, this is another plate, conducting plate, and these are separated by some dielectric materials, right? So these two plates, across this one, if I apply one voltage, and that voltage is suppose VC, then you will see here some positive charge will store, and this side you will get negative charge. Okay, and the charge stored in this capacitor Q is basically proportional to this voltage applied to the capacitor VC. So we can take equal sign. In that case, Q equal to C times VC, and C is called capacitance of this capacitor. So this is the basic lesson, Q equal to CV, right? So in short, what you can say, this capacitor as it is a energy storing element. Okay, and this energy is stored in the form of the voltage. It will first store the voltage. Okay, and second one is that the capacitor is a frequency selective element. Right? So these are two important properties of capacitor. It can store the charge, thus it can store the energy, and its behavior is changing with different frequencies. That will be discussed in detail later. Right? Now it will have several applications. So these are few applications I have shown here. As I told you that it's a frequency selective element, thus we'll consider this capacitor as a basic component to design filters like low pass filter, high pass filter, band pass filter, band reject filter. So any sorts of filter we can design using capacitors and resistors. So we can go for active filters or passive filters, right? We can use this capacitor as coupling element. Basically, it is between the biasing circuit and AC input. So biasing circuit is used to make the device, active device, in working condition. These sources are applied there. And when AC input is applied, then so that this biasing is not disturbed, thus capacitor is introduced. And here capacitor is using as a DC blocking capacitor. So here main thing is that it is behaving as DC blocking. Okay, so capacitor, I told you that it is a frequency selective element. So if I consider DC and AC, it is a high frequency. If I consider So for DC, capacitor is behaving as open circuit. It's open. And for AC, it is behaving as a short circuit. Means in AC circuit, the capacitor will produce very low impedance, whereas for DC, it will provide a high impedance, almost infinite. Thus, it is behaving as open circuit. So it will block this DC. Okay. So AC component can pass through this one. So when AC is applied, but DC is not disturbed. Okay, biasing circuit is not disturbed. And it is also used for different kind of wave shaping circuits like clamper circuit, oscillator, where we get some sinusoidal oscillation or square wave. Okay, so there we can use it. So we'll be discussing those three applications in later. Now, first we want to get basic relation in capacitor between voltage and current. So as I told you that in the capacitor, the voltage is Vc and current is Ic, right? So this charge is suppose Q. So I've told you that Q is the charge stored, that is given by C times V. So the current I, we can write, is a positive charge we're considering. So change of this charge dq dt will give you the current. So in this case we will consider Vc, and current I will consider Ic. So Ic equal to dq dt, and C is constant outside, so it is dVc dt. So this is one important relation, Ic equal to C dVc dt. Okay, so what is happening if we apply one DC source with this capacitor? So this is your capacitor. Suppose we through one current limiting resistance, if we apply a source here, okay, so this is a negative terminal. So from here electrons will be generated, and that will go through this side, and those electrons will be stored here. Thus you will get negative charge here. Okay, and here the again electrons are coming from this side, and you will get a closed path, the flow of charge, electron charge. Okay, so this is the electron flow. So here it's absence of electron, so you'll get a positive charge here. So thus across these plates you will find the charges. On this side you will find positive charge, this side you will get negative charge. So how long it will continue? Okay, that is one question. So at steady state you will see that this capacitor is fully charged. So here we'll have two concepts. One is charging, other one is discharging. So when capacitor voltage is growing, that is called charging, and when capacitor voltage is reducing, that process is called discharging. So in this here in this configuration, capacitor is charging up, and it can attain a final voltage, steady voltage. Okay, so that voltage, if this voltage is capital V, that I'll discuss later, so full voltage will appear across the capacitor. Okay, okay, now let us consider one basic concept. Now, now suppose in this capacitor, if we apply this kind of voltage with the time, so this voltage Vc is varying over time, and that is applied across the capacitor. So you see it is growing, and then it is becoming constant. So as you know, the capacitor current IC C dVc dt. So you need to take derivative and multiply with C. Okay, so as it is a linear curve, okay, it's rising curve, so its slope is constant. So we can plot the IC1. So this is the IC. So you see from 0 to capital T, you will get a constant because derivative is constant. And beyond that, when T is more than capital T, this Vc value is constant, so derivative is 0. So here derivative is 0 and here it is growing linearly, thus derivative is constant. Okay, and this constant value we can find out. So it is something but a slope. So this height is capital V, this axis is this time is capital T. So slope is V by T. So dVc dt is V by T, and we have to multiply by C. Then you will get exact current. So this value is C V by T, right? But when T is more than capital T, then it is flat, VCT is flat, so derivative is 0, it is not changing, thus its value will become 0. Right? So it's very simple. Now second on this one, second example, if we consider. So you see, when T is negative, then it was 0 here. At 1, it is suddenly changing to 1 level. So here slope is infinite. Suddenly it is changing. So derivative is infinite. Thus this IC will contain one impulse here. Okay. And then, so that impulse I'll consider it's a 1 unit change. So I'll call it del T only, delta function. And then from 0 to 2, it is a constant. So its value is 0. At 2, it is changing from 1 to 3. So 2 unit change, again positive change, again one more impulse. So that value will consider 2 del T. So not del T, I'll consider del T minus 2. It's located at 2. Okay. And then 2 to 4, again it is 0. The derivative, there is no change. Derivative is 0 here. But here there is certain change from 3 to 0 at 4 level at T equal to 4. So here you will find another impulse, and that value will be 3 times minus del T minus 4. Where it is 2, it is 4 with respect to time T. So what is the meaning here? What I want to mean here, that when capacitor voltage is continuous, okay, the derivative is finite. But when capacitor voltage is changing suddenly, like here, it is changing suddenly, or here, then you will find a huge current through the capacitor. Okay. So whenever you will find a sudden change in voltage, you will find infinite current across the capacitor. Okay, so that you can conclude, for sudden change in VCT, what you will get, ICT is approaching to infinity. Okay, that is the important conclusion here, because sudden change will imply that infinite slope. Okay, right. Now I'll consider practical RC circuit. So when this capacitor is introduced in resistive circuit, we'll call it RC circuit. So in RC circuit, we'll expect that the VCT or rather ICT is finite. It is not going to infinity anytime. Okay, if we consider in that way, the circuit is not having infinite current. It is stable circuit, right? So if ICT is infinite, in that case, we can say that ICT equals to C dVc dt. And C is constant. This will imply that dVc dt is also finite. And what it implies? This implies that VCT is continuous function. Right? So derivative will exist. It's a continuous function. And it's imply that so that at any time at t equals to capital T at any time, so VC at t equal to t minus what was the voltage across the capacitor, just after that one t equal to t plus, you should get same value. There should not be any sudden change in capacitor voltage. Okay, if we assume that, so this is our assumption. So in practical circuit, we are assuming that IC is finite. So if IC is finite, then what you will get? VCT is continuous in time domain, means at any time, so it limit will exist. So VC at t equal to t minus and VC equal to t equal to t plus, you will get same value. So this concept is useful in switching circuit. Suppose if I have one circuit like this, one voltage source, one resistance, and there is one resistance and another source. Okay, this is this one and this is a capacitor. Okay, so this capacitor voltage is VC. This is your capacitance, this is the R, and here this is one switch. So this switch is turned to this place from A to B at t equals to suppose 3 seconds. Okay, so what will happen? So though this switch is changing from A to B, the capacitor voltage, what was the capacitor voltage at 3 seconds due to this circuit? Okay, this source, it was connected, and for that you will get certain voltage across the capacitor. So this capacitor voltage at 3 seconds, what was the voltage level? And it will continue from that point. Okay, it's implies that VC at 3 plus, it should be same as VC at 3 minus, so T equal to 3 minus. So you should continue from that point only. There should not be any change in capacitor voltage. Right. Now, this RC circuit, if we consider in steady state, when DC source is applied. So at steady state means, so when all the elements will converge, the current and voltage will become steady. So we can assume that when DC source is applied, I can expect this IC T is becoming constant and VCT is also constant at T tends to infinity. That we are assuming. So what is IC? IC is C dVc dt. So if Vc is constant, what will happen? Derivative will become 0. So derivative is becoming 0. So that imply ICT IC at infinity, it should be 0. So current through the capacitor is becoming 0 at steady state. What it implies? It is open circuit, because in open circuit there is no current flow. So capacitor is behaving as an open circuit at steady state. So capacitor behaves as open circuit at steady state. This is important information, okay? So we can replace the capacitor by this open circuit. It's open, right? So you see, we'll be using this concept to find the steady state value in a circuit. Let us take this example. Okay, so you see here, this is a switch and it is turned on at t equal to 0, and this circuit is containing 2 ohm, 8 ohm and 1 farad capacitance. It's a 10 volt source. So we need to find out Vc at infinity. So what we'll do, we replace this capacitor by open circuit. So we'll redraw the circuit. So this is closed, this is resistance, and this is the resistance, and this one is open, because capacitor is behaving as open circuit at t approaching to infinity, right? This is your 10 volt, it is 2 ohm, this is 8 ohm. So what is the potential across this one? This 8 ohm resistance, and that will be the same potential as across the capacitor. So this potential is same as Vc infinity. So Vc infinity will be, now it is a potential divider circuit, a series circuit, 2 ohm, 8 ohm are in series. So across 8 ohm is 8 upon 2 plus 8 multiplied by 10. So it's a potential divided, it's 8 upon 2 plus 8 multiplied by 10 volt. So you'll get 8 by 10 times 10, 10 cancel out. So it's 8 volt. So finally 8 volt is stored across the capacitor. You won't get 10 volt because of this circuit. Okay, so at least that thing we can understand. So what would be the final voltage across the capacitor for this circuit, right? Now take different example. Now in this example, this switch is opened at t equal to 0. This arrow is given, no? This so that earlier it was closed, now it is open. So when it was closed, how long it was closed, it is not mentioned. So we'll assume that from minus infinity to t equal to 0, till that time it was closed. So by that time, obviously capacitor is fully charged. So be careful here. So I am assuming that this circuit was closed for a long time, from minus infinity to 0. So circuit was closed from t equals to minus infinity to t equal to 0. Okay, so this is infinite time. By the time capacitor is fully charged, so capacitor is now steady state. So we can make the capacitor open circuit, right? So what we will do, we'll replace this circuit. This is closed, this one and this one and this one. Okay, this is a 20 volt source. Now it is 1 ohm, it is a 4 ohm. So what is the voltage here? So this is open, capacitor is made open. So this voltage Vc, it is now steady state, but its time reference is 0. Okay, so VC at t equals to 0. Rather, you can write t equal to 0 minus if you have some confusion. Okay, so that value is 4 upon 1 plus 4 times 20. So it is 5 into 4, 16 volt. So that is same as VC at t equal to 0 or 0 plus. Same. Right? And what would be the derivative dVc dt at t equal to 0 plus? Now to understand that one, so if it is open, this is open, what is circuit? Only this is circuit. So in this circuit, so what you can do? So now circuit is t more than 0. That time we'll consider circuit. This is a capacitor and this is the resistance. And left side circuit is open. So 1 ohm is also open circuit. Will not consider. So this is the 4 ohm. And this is your capacitor. 2 farad capacitor. Okay. So voltage is VCT. Okay. But at t equal to 0, its value was 16. So if this voltage is 16, okay, so what is the current through the resistance? That is your 16 by 4 means 4 ohm. So this current is IC and this current is IR. So IC equal to IC at 0 plus will be minus IR negative side at t equal to 0 plus, and that value is how much? Minus. So this is your 16 by 4 equal to minus 4 ampere. So this value is dVc. So this dt. So you see C dVc dt is IC. So if you divide by C, so it will become, this is 4 upon 2, that is your 2 volt per second, right? And now VC at infinity, for this circuit there is no source, so now capacitor will discharge the current, and you see the current is negative. It's implied that actually it is discharging, current is flowing in opposite side. Okay, so negative sign indicates, so this dVc dt negative. Okay, you should put negative sign, don't forget, it's a negative sign. So the negative sign will indicate that its value is reducing. Okay, so at infinity it will become 0. So there is no source, so at infinity there is no supply is there, so its value will become 0. That's simple. Now I'll give you a small homework problem. So you see, in similar circuit, just it is made open at t equal to 0. So I have included one more resistance 6 ohm here. So can you find VC at t equal to 0, dVc dt at t equal to 0 plus, and VC at infinity? So please post your answer in the comment section. Okay. And if you enjoy this video, please give like and share with your friends. And you may subscribe my channel. And to subscribe my channel, first press the subscription button. And then don't forget to press bell button, because then only you will get immediate notification of my future videos. I hope you are going to subscribe my channel, and I will be uploading lots of videos in this channel. Please keep watching. Thank you.